Hello, I'm Adam Root, Research Scientist and Technology Lead at NVTrace LLC. Thank you for the opportunity to share our work on tracing dynamic objects in spatiotemporal flow fields, a scientific AI capability with broad applications in defense and industry. NVTrace LLC delivers cutting-edge AI solutions for complex science and engineering problems. Our team combines over 100 years of experience in AI and fluid dynamics with more than 500 research publications and over 20 open-source contributions. We've secured over $3.5 million in non-dilutive funding through 5 Phase 1 and 2 active Phase 2 SBIR awards, and we hold patents and R&D 100 awards for innovation in AI and scientific computing. Key team members include Trace Kliphaus, CEO and co-founder with a background in chemical engineering and state government executive-level leadership. Velimir Monty-Veslanov, CTO, former Lanel scientist, and a pioneer in AI for Earth systems and multiscale modeling. I am leading the development of this technology, and I bring over a decade of experience and innovation in scientific machine learning, particularly for nonlinear dynamical systems. We also maintain collaborations with top-tier national laboratories and academic institutions, ensuring our technology and transition pathways are validated across both basic and applied science. Our team isn't just technically capable. We understand how to execute in mission environments, deliver on government contracts, and translate deep tech into operational tools. Tracking moving objects such as plumes, eddies, or vehicles is a long-standing challenge in fields like fluid dynamics, weather prediction, and situational awareness. Objects of interest in these systems can vary widely in size, shape, location, and orientation. They may have short lifespans, appear infrequently, and be significantly underrepresented in data. In many defense and scientific scenarios, we don't know in advance what patterns to look for, or even that they exist. The current state-of-the-art in computer vision is largely based on supervised machine learning. These approaches need large amounts of label data and are only as good as the features they're trained to recognize. By construction, they cannot detect truly new or rare features. Our disruptive solution advances the state-of-the-art through a universal unsupervised machine learning framework known as the local causal state method. It breaks the limitations of supervised learning, as it does not require label data or handcrafted feature templates. Instead, it reconstructs the underlying causal structure of complex systems directly from data, enabling the automated discovery of coherent spatiotemporal patterns, regardless of size, shape, or prior knowledge. This allows our framework to detect and track never-before-seen features or anomalies, to track rare and high-impact events like hurricanes or adversarial movement patterns, and to generalize seamlessly across application environments and objects of interest. Our method has demonstrated scaling on HPC systems for training, and Inference can be run with modest compute, making it suitable for real-time field deployment. We also recognize challenges ahead. The current implementation has memory-bound scaling that requires HPC systems to run on large real-world problems. While technically feasible, we have not yet implemented field-scale deployment to deliver real-time streaming insights, and we have so far worked with clean model output data, and need to add measures to ensure robustness to noise and uncertainty. That said, our architecture and prior work have already shown strong results in addressing these hurdles, including successful field tests on large weather and fluid systems. We are also exploring forecasting capabilities so that we can additionally predict the future trajectory of tracked objects of interest. Our solution has high-impact applications across both defense and commercial sectors. In defense, our tool can support ISR and threat detection by flagging novel emergent behavior and sensor data, including electro-optical infrared, radar, and acoustic, without needing labeled examples. It can also improve mission planning through automated tracking of extreme weather and ocean conditions, including biohazard and contamination plumes. In the commercial space, our tool is already being positioned for weather and infrastructure resilience, detecting high-impact weather events that are increasingly critical for utilities, insurers, and city planners. It is also useful for energy and environmental monitoring, enabling scalable, data-efficient tracking of contaminants, hydrological shifts, and subsurface flows, especially in carbon sequestration and groundwater systems. Here, we demonstrate the ability of our technology to track hurricanes and high-resolution weather data. The local causal state algorithm automatically decomposes complex systems into a finite set of local behaviors, and each point in space-time is assigned to one of these behavior classes. The motion of objects of interest yields specific spatiotemporal behaviors that in turn are associated with a unique set of classes. Because the classes are assigned at each point in space and time, tracking happens automatically once the classes of interest are identified. In this case, we identify the set of classes associated with hurricanes, and any point assigned to a hurricane class is highlighted in red. By contrast, the standard supervised approaches required labeled training data. This of course means you can only track known objects that you've previously labeled. But even for known objects of interest, it's not always easy to generate these labels. Hurricane labels, for instance, require effort from domain experts, and they may not necessarily have time to devote to labeling, and even then they may not always agree if a particular event should be identified as a hurricane or not. Hurricane trackers of course do exist, and those used in production are unsupervised in that they do not use label training data. However, they are very specialized and based on specific meteorological heuristics. So, like supervised methods, they can only track what they're designed to track. These hurricane trackers, for instance, cannot be used to track contamination plumes, say, in the ocean. The breakthrough of our local causal state method is not that it can track hurricanes, but that it can do so using a universal structure principle. While we can fine-tune the algorithm using domain knowledge, the same general algorithm can track objects over a wide range of systems, including other complex fluid flows, but even abstract mathematical models called cellular automata. Moreover, because it is a general unsupervised method with essentially no prior assumptions on structures of interest, it has the ability to reveal and track hidden and elusive objects that we may have not even known were there. Thank you for your time. We are excited about the potential of this technology to deliver real-world impacts across both national defense and environmental resilience missions. We welcome the opportunity to work with you and explore next steps.